welcome to our first talk. It's held by EWB. Thank you for Professor Tony Marmont, who's come in from Loughborough University to talk to us. I don't know if some of you have seen Beacon Energy, his company, and some of the things he's done. I'll hand over straight over to him and we'll hear him talk. There's PDR points if you want your book signed at the end of the talk. We'll be outside. Thank you.
Well, hi folks. You've probably been looking at the slide on the screen, and that's our home, and you can see a diversity of different forms of energy there. And over the last 25 years I've been experimenting with all these things and culminating in the production of hydrogen and fuel cells. So I'd really like to talk about where our energy will come from in 2015. It's quite a serious question. It's not just the question in England of the decline of the nuclear power stations, the closing of the coal-fired power stations, which is important, but it's all over the world because we have an increasing number of people and we have an increasing use of energy and we have a finite source of energy. So I want to talk about that. I want to talk about climate change and how that can affect what we do. And then I'll put to you a question about what I think we could do with it to try and put the matter right. That's a big question, and one person, one company can't do it. But it's worth thinking about all the things that we can do to put it right. Engineers Without Borders, I like that title. I didn't know what it meant until I asked Elaine, but it seems to me that if you really do work in that way, and you do cross borders, and you do teach engineering, and you encourage in all sorts of people and get cross-referencing and so on, that's excellent. So many times people don't seem to learn in the science, the physics, and engineering, electrical and so on. There's more sexier things that come up. So I'm so pleased to see you're all here. Right, the A380, how is it going to be fueled? I mean, it's got to have jet fuel. So that's something that has to be thought about. Now I'm going to touch on climate change. This is a picture of the Andean glaciers. The top picture is what it was 25 years ago. The bottom picture is what it is now. And I think, oh, can you see? Yeah, in the way. No. It's a heck of a change. And it's not just there, it's in the Andes too. And you see, I think you already realise this, that the snow that accumulates on top of the mountains is the source of water during the summer, not only for drinking but for irrigation and food. So if this all begins to melt in the way it is shown on those pictures, we have quite a problem to face up to in the production of food and water. Climate change. Here's another example. In the Antarctic, the Larsen ice sheet broke up. Those pieces you see drifting off are not little tiddly-windies, they're the size of some countries. And we all thought it would not happen for many 20 or 30 years, but it didn't. It broke up in a matter of months. And when you look at the Arctic, the other side of the world, you can see the decreasing level of ice, the darker colour, the grey and the white. And this year is the worst ever, and I haven't got this year's pictures yet. It will only be for 2010, of course, not 2011. But it's expected to be 25% worse than that. And by that I mean the white portion that's left. So, this is the movement of ice, and that's another thing we have to regard. The deeper the colour on that slide, I must have in the way. I'll sit down, how about that?
You can't do that.
Yeah, I can still see. The deeper the colour on that picture, the faster the ice is moving towards the coast. And it's 4 kilometres thick, and the ice is being cut through with descending tubes of water which provide lubrication to the ice. Now, we talk about that, and we talk about what's going to happen when all the ice disappears, and I'll come up with that later. But here's an interesting graph which I'm sure you're aware of the relationship between CO2 and temperature and the effect on the planet. And you see, if you look at that line there, the red line at the top, that's the global temperature, this one here. And if you look at the Arctic open water anomaly, which is the temperature of the Arctic water, you can see the purple line is going and following it. And then if you overlay that with atmospheric CO2, which is the brown line, and here it is, the brown line here, and actually they're almost identical, aren't they? So it's a pretty staring example to us that we have got a relationship, and yet there's still people in the Flat Earth Society that don't believe that climate change is happening. And mostly my age group, I have to say. Now, I've taken just the rise in sea level which would occur if perhaps the Greenland ice were to melt, and you can see in here that's a 6-metre sea level difference. So it's taken away most of the Low Countries, most of England's eastern side, London's, places like that, House of Parliament, hooray. And the thing is, for every 1 centimetre, I'll read my own notes here, for every 1 centimetre sea level rise with floods, there is also 1 million eco-refugees. And you know from the Pacific Islands they rely very heavily on a meniscus of water, and it's only a couple of feet thick. And when the sea level rises, it gets into that, and salt water, and plants won't grow, and they've got no water, and so on. So all over the world there's people going to be migrating, which is adding to the problem of resources. Here is London City, and they've got these Thames barrier which has been put in, and it was built in 1984. Can read that just from here. And you can see the trend of the number of closings. Now the closings are designed to stop the sea entering London when there's a high tide, there's a high northeasterly wind in the North Sea, and so the whole impression is gathering up the channel into London, up the channel, the Thames Channel. Well, just recently we've had several 1 in 100-year anomalies of floods, and there's been, the Thames runs through Oxfordshire, and this has been a problem. Every time there's been one of these massive floods, it's got away through the river, and it's going down and escaping through these gates because they're open. But you imagine a situation when you close the gates because there's a high tide and a high northeaster wind, and now the river goes into flood. What happens? I don't know. It's going to flood London, isn't it? Here's the number of wind farms in Britain, which is beginning to get a grip on the situation of CO2 emissions. We have a large number of wind turbines, but I must say it's nowhere near as much as they have in Europe. But we have, you know, a total of 670 wind farms and 23 megawatts of power. In the EU Economic Union, they've got 100 gigawatts of power, and that's equal to 39 nuclear generators. Now, look at that picture of that thing at the top. Wind will well surpass nuclear in 2013. And this is where the critics say it doesn't, because it's intermittent. So yes, it's intermittent, but yes, you take the cake when you can eat it. And if you can't take all the cake, you have half. And that's what it boils down to. So you're going to have another form of energy generation and a form of energy storage. I'm going to move on to that later. Remember, if you're just using wind or tide or sun, the cost of the energy, the basic fuel, never goes up. So you've got a fixed, in anti-inflation, anti-OPEC tool. In my own house, I've done what I preach, and that is we don't have any water supply, we don't have a pipe. So I've had to collect my own, and I collect off the roof. And 97% of the Earth's water is in seawater. And that's a sobering thought, because to get seawater into fresh water, enormous energy. We've got 2 25 kilowatt wind turbines, which I built myself, and they generate between 40 and 50 megawatt hours a year. So it's not inconsiderable for one little farm. We export, of course. But then there's the question of building, and this will come partly into your course, of course, in the form of engineering in buildings. But when you have a conventional house and it gets cold, the heat loss escapes through the walls and the roof. It soon gets cold. But in the summer, a conventional house is just the opposite, isn't it? It picks up heat from the outside and it gets hot inside. And then you have to install air conditioning, and that's another form of energy, which is another form of CO2 emission. Now, if in the construction we can put a triple insulated housing, that is 3 times the insulation that the architects want, we have a very stable temperature all year round. You don't need any heating or cooling at all, and you can have a minimum spend on renewable energy technologies, because they're not cheap. So why spend it if you don't waste it? What we've done at my own home is just that. You can see up here, we've put straw bales on the outside of the existing home, which was there, and then put another layer of windows and straw and stucco, so that we have a really, and then got 4 layers, 2 double glazed panels, making up the insulation of the windows. Very good sound barrier, because they're that far apart from each other. Bale of straw in the middle. And so far it's working very well. We've got quite a small heat pump which heats the house, and hot water and so on. Another thing that's an anomaly in renewable energy is that most of the wind turbines in the world fail when the grid fails. They don't run. Well, I would have thought we had to have something that when the grid wasn't there, we had wind energy. Not so. And the same with solar power. So we designed and built this at Loughborough University, this box here, and this allows my 2 wind turbines to run when there's no grid. It's not expensive, it's not complicated. So there's an enormous business opportunity for somebody to retrofit the world's turbines with a standalone device to enable them to run when there's no grid. Of course, the grid's got to be sorted out too. Those of you who are doing electrical engineering know that that would be another problem. Yes, that's true, and that's another thing to be solved. I've got solar panels, and this is part of them. I've got about 14 kilowatts of solar panels altogether. This is 3 of the kilowatts. And this is used solely in water pumping from below ground. When we talk about that water pumping there, most of you would probably not know the fact that when you pump water from below 11 metres below ground, I was just explaining this to Elaine as we came in, the water is at a constant temperature of 11 degrees C. So if you want a free air conditioning, you don't have to put vapour compression, electrical gases with CO2 or whatever you're going to use as the refrigerant. You can just use water from the ground, pump it out, pump it into the stream, pump it into the lake, whatever source you've got, and it'll provide cooling for your house at no energy cost and no earth cost. Terminal 5 is done like that. At my behest, when I went to see, and I was very pleased, the chief engineer in charge of the construction of Terminal 5 was a lady called Liz Southern. I think that's marvellous that she got that job. And she carried that through. And now London Water Authority pay her for every cubic metre she extracts because it reduces the water table. So you see the benefits of using alternative technology can be exploited. I moved into fuel cells and hydrogen because I had intermittency. I wanted to overcome the intermittency, and it did. And this is a hydrogen electrolyser which I had. I've now donated this to Loughborough University, and it's been formed in a special section. Got a hydrogen refuelling station there, and it's green energy because it's made with energy from green purchase. When I had it at my house, I stored the hydrogen in big cylinders. And then this is the interior of a fuel cell. And you see that up there, that's the actual fuel cell. It's a stack of plates, stainless steel with acidic polymer membrane in the middle. But most of the works are electrical to deal with it. The problem I found was that all the fuel cells worked, but I didn't get my loss of intermittency because they failed every 400 hours. The acidic polymer membranes failed. And when I asked the manufacturers, they said, well, we can't do more than that. Well, 400 hours? Crikey. And I changed them and bought new ones at £7,000 ago, 3 times on 3 fuel cells. The best was the Horizon from China, but that did 1,000 hours. So I decided it wasn't practical at the moment, which is why I hit on this idea of fuel for aircraft. That's my aircraft. And I fly it, and I've got a guilt complex about the CO2 emission, but it's nice to fly. So I decided to look into what we could do, and I've been working about 15 years ago with British Airways and with Rolls-Royce on producing a synthetic fuel from biomass. And yes, it could be produced, and yes, it was cost effective. But I soon realised when I got stuck thinking about it, all the stuff you're using, apart from waste biomass, which is perfectly okay, but once you start taking crops, you're putting the price of fuel up, you're reducing the availability of land, and the population's increasing at the same time. So I didn't think it was a good idea, long term. So I started to think how I could do something. And so what I did, I took a very unusual step. I had a gentleman join me who, Dave Benton, who was a nuclear physicist at Alderman, Baston. He'd been making hydrogen bombs all his life, which you might shudder at. And I said to him one day, what does it feel like to be working all your life and never having used one? He didn't think that was funny. So the fact is that he got enough knowledge and I got enough knowledge, and between us we concocted an idea. And that was, the air contains CO2. The air contains water, anything from 80% to 30% in the desert. So with those two materials, if we could extract them from the air, we could make the carbon from the CO2 react with the hydrogen to produce a hydrocarbon fuel. And we had a go at it, and surprisingly, it worked. Now all the pundits said we couldn't do it, but you see how it's done there? We've got wind turbines providing the energy. We then go into a filter which collects the CO2 from the atmosphere, and the energy also goes into the... I've got some handouts, but I haven't got enough for you all. I didn't think this one this many here. And then it goes into a standard hydrogen electrolyzer and produces hydrogen, and then we react the two together in a catalytic process. And it's exothermic, which those of you who have any knowledge of chemistry will know. It produces its own heat, and it runs up to about 200 degrees C, or more if you don't cool it. And we shall use that heat when we have a production plant as part of the plant process to produce the energy. Okay. Well, we decided to build one, and we didn't have a lot of money, so we bought some old containers, sea containers, and we used 3 of them. And we built, first of all, a CO2 scrubbing tower, and I'll explain how that works. You've got the scrubbing tower here, and you've got the hydrogen electrolyzer here, and then storage tanks for the hydrogen and the carbon dioxide. And then here we have the reactor. I'll show you some pictures of it close up. The scrubber demonstrates very simply, if you take sodium hydroxide, which is caustic soda, and you spray it down through a tower, with a gentle updraft of air going the opposite way, and finely atomized sodium hydroxide. Not a big pump, not a big energy cost. Well, then it becomes sodium carbonate. And sodium carbonate, baking soda, and so you put it into a tank at the bottom of the tower, and you take it through an electrolyzer, which is a tri-cell electrolyzer, and it produces 3 gases. It produces CO2, it produces hydrogen, and it produces oxygen. So now, we think we can get that to work to get the stoichiometric level of CO2 and hydrogen at the ratio of 3 to 1 to give us a standard fuel without having to electrolyze as well. We haven't done that yet. We're electrolyzing and we're collecting the CO2 and chucking the rest of the stuff at the moment. But that's because we're in a test mode. Okay. A bit more about the schematics of the building. This is the bottom of the collecting tower. And these are the flow gauges we use to measure the speed at which it's travelling, because it's critical that you get your speeds right and the energy right. This is the unit which produces petrol. Now we produce petrol. In fact, yesterday I was riding on a motorbike which was fuelled with the petrol we made. And what happens is that in this case, the methanol, which we produce as well, part of the other process, comes into this reactor here, this one, and there's a series of catalysts in there which turn the methanol into fuel, and that fuel contains some jet fuel. Now, not sufficient. We will have to make a special run, a special machine, a special tube to produce jet fuel for aircraft. The amount we're producing, of course, is insignificant. We're producing 5 litres a day. But when we get into a 1 ton a day plant, or 10 ton a day plant, or 1,000 tons a day plant, it's a different kettle of fish. You don't want to do that till you've built a good unit that works, to make sure it does work, because it costs money. So this is the interior of the other building, shed. And this is the reactor for methanol, this one here. And then these are the collecting condensing cylinders. And these two are the compressors for the hydrogen and the CO2. That white one is the electrolyzer producing hydrogen. We've got a peak in fossil resources, we've got climate change, we've got environmental crisis, we've got a UK energy security problem, and we've got commercial opportunity. Now put all that together, I can't understand why we can't get this going. We haven't tried seriously. We've been doing the experiments. It's only in the last 4 weeks we've actually produced petrol. So when I was asked to come, I thought, well, it's good because you can hear the story firsthand, what happened. And when we look at here, we see another point, is that you've got countries like China and India and Africa and Asia that are all wanting and are getting the same standards of living. Well, I hope not the same as USA, but perhaps the same as Europe. Europe uses about 18 barrels of oil a head a year, USA 32, China uses 4, India 4. If they come to our standards, this is a shocking point. Oh, sorry. I'm not criticising China at all, because they do a lot to try and ameliorate what they're in for. But they alone will require 89% of the existing world oil. So that's without it running out, just demand. So will there be enough for the rest of us? Because India is going to want more, Africa, Asia. We've got a rising economy too. I'll talk about the drivers from having a constant growth in gross national product, which is not my scene. I think that's a wrong thing. We shouldn't be doing that ever. But still, I'll tell you what I think. So oil underpins everything I do and you do. The tarmac on the roads, the concrete curbs, the lamp standards, the car steel, everything we do. This building, made of oil. Why are we better than other fuels? Well, one thing is that we're better than electricity as batteries at the moment because the energy density is a lot higher, and it fits the existing infrastructure in being a drop-in replacement, petrol, diesel, Jet A1, methanol, and incidentally we can make fertilizers and plastics as well, and pharmaceuticals, and so really a very versatile fuel. So if you imagine the 747 carries 50,000 litres of fuel, and that's 500 megawatt hours, well that's more than enough to drive a big city. So that every time a 747, and there are how many of them flying? Hundreds, is using that sort of energy. Now, synthetic fuel qualities. It's above that of conventional diesel. It's above that of conventional petrol. The analysis of the petrol we've got is far superior to anything on the market. Because it's pure, it contains no sulfur, to a constant measure, it's not like a variation from every oil well. The sulfur dioxide reduction is huge. The emissions reduction is complete, it's just a neutral fuel. It fits into the distribution system, CO2 neutral, enhances energy security. So, if we look at the energy density graph, you can see at the top end here, you've got fission and will be fusion. And then next to it, coming down the scale in density, you've got coal, oil and biomass. And finally come down the scale to all the different things that we're playing with at the moment. But the most energy dense we can get next to fission or fusion is oil or coal. So if we can find a way of producing synthetic oil, we're into the top band of energy density. Though I have to say some of the new general aviation aircraft, the light ones, the 4-seaters, which started at 10 minutes flight with batteries, are now up to 3 hours. So there's some potential. We talk about the moon. H3 exists on the moon in big quantities. H3 is a huge benefit for the fuel system. How can we get it back? Something for you guys to sort out, not me. So when you go into business, you've got to think how we can go to the moon and mine that H3 and bring it back. If we can, it will be very helpful to our energy system. And of course, if the fusion reactor, which is working now in Oxford, the tokamak, and also the ITER project in France, which is a national, they claim, but then they claimed that 25 years ago, they claim that in the next 25 years they'll have fusion power. Well, we can see it working because the sun is an example. We haven't got it yet. Just as an example, I've got a colleague in the Northern Arizona State University, and he and I worked together on many projects. And his graph took a very awful result, really, of his analysis. This column here, oops, sorry. This column here is what USA consumes in oil. And this is what the rest of the world consumes in oil. All put together. Now, doesn't that make you think? It's very uncaring and greedy. And so we have to somehow educate the Americans to begin to think about other people, not themselves.
Good luck.
You can try. They don't even, Andrew went to a school in Arizona, an Indian school. I went to a red Indian school, and she was talking to them as a teacher. And one of the children asked her, "How do you get here? Do you drive?" Well, of course, there's a big Atlantic Ocean in the way. Didn't know that. We can consider our fuel to be a carbon sequestration tool too, because if you were to take it and you could make enough oil, if you were rich enough to make enough oil more than you wanted, and anyone know how much oil Britain uses a day? Well, I'll tell you, 140,000 tonnes a day. Whew. If we could produce, let's say, 20,000 tonnes a day above the requirements we needed, and we took it back to the oil wells in the North Sea, which are now empty, we could bury it. Now that would be secure sequestration, but it would also be a very convenient source of energy storage, because if the Earth's temperature started to fall as a result of the CO2 level falling, at the moment, you know, we're about 380 parts per million. Well, the ideal is probably 310 or 300, and that's what it was before the Industrial Revolution. So we might bring it down to 300, but it might continue to go down. Now, if it did, we'd be into an ice age, and I'm not suggesting that we want to start geoengineering, because that's fraught with all sorts of difficulties. But you could bring some of the oil out of the oil wells and use it as a means of controlling the temperature. Just a thought. This is the process in schematic form, which I've described to you. And you can see the tower, which is having the spray droplets. You can see the collector of sodium carbonate, and the hydrogen electrolyzer, and the two reactors for fuel. It's not complicated, it's very simple. We use the sodium hydroxide stripper, and it's not our invention even. David Keith at Calgary put that unit up in 2005, and there are various people using CO2 collectors for buildings that contain plants, you know, these ploshes, agricultural plants, cultivation. So we've taken existing technologies, we haven't invented it. What we've done is put them together, which no one's done before. And this was another chap who helped us. His name was David Fletcher. And he invented a system of the tri-cell electrolyzer, which I mentioned to you, produces the gases. And we've used that. And you know what the principle of electrolysis is. You've done it when you're in primary school. 2 carbon rods in water, hydrogen carbon coming off with the DC current. Now this chap, very interesting. This one, Reginald Mann. Unfortunately, he died because just after he started working with us, because that was one of those things. But he said he was working at Castrol Labs in Pangbourne in the 1970s, and a Fischer-Tropsch plant, which is a reaction of CO, carbon monoxide and hydrogen, was running. And inadvertently some CO2 got into the process line and it went much better. And that gave us a clue. So we thought, well, we can probably react CO2 and hydrogen together, and I can tell you we can. Now, I talked about energy. So when we look at the energy that's involved, and nothing can be 1 for 1, take it for granted, you cannot do that. We're about 2 and a bit to 1, which I think is very good because most energy conversion factors are usually more. Your car is 18% efficient. Power station's probably 30% efficient. So we use, in terms of, if you take that the energy content of petrol is 9.7 kilowatt hours per litre, that's a measure. If you take, well, we're using 0.44 to collect the air, we're using 4.6 kilowatts to release it with the electrolyzer. And you go down the scale there, the actual electrolyzer here is exothermic, so it's actually giving energy out, and that's a benefit to it. The total energy we use 21.38. So you could say it's a ratio of 2.2 to 1. Now, we've only just started. You can't tell me that when the oil industry started in 1880, they were as efficient as they are now. I doubt it. And oil was extremely expensive, and it was cheaper to use whale oil, which was really sustainable. And so we think that probably in 20 years' time, when this process is pretty well universally adopted, if it is, that the energy efficiency will be improved on that. I personally believe that we can get down to 1.83, and others believe even lower, but I've yet to prove it, we can't. I mean, we're still working at it. This is the carbon neutrality cycle and in producing synthetic fuels. And everything is from and to the Earth, and it's fed entirely by the sun. There is no drain on the Earth's resources whatsoever, and no addition to the Earth's atmosphere or sea or water or land. Because if you can imagine, you make a synthetic fuel from CO2 captured from air, you put it into an aircraft, you burn it, you release CO2 and water. So you're releasing the CO2 and hydrogen back to the atmosphere. Well then, somewhere else, 100 miles away, you're collecting the CO2 and hydrogen in the same quantity, feeding it back into a reactor, and it's a virtuous circle. And if we could do that, it is a fact that the Earth has a tremendous absorptive capacity of CO2, particularly the sea, and also the land, the soil. So at the moment we're chucking CO2 into the atmosphere so fast that the Earth can't absorb it. If we could stop chucking it in the atmosphere and just stay neutral, not sequester it, just stay neutral, the Earth would on her own account recover it in 20 years. So we have a challenge there, and that's something we can think about, because I'm worried for you and your children, because what's going to happen is unthinkable in terms of temperature rise of 3 degrees or 6 degrees centigrade. A bit more detail about the process than the rather vague schematic that you saw earlier on, and those of you who are interested might find it interesting. I think Elaine said that this will be available afterwards, won't it, this talk? There's a number of slides on there which are not here, which are relevant to other audiences I gave, but you might find them useful if you look at them. This is the area of land that I calculate we'd need to replace all the 140,000 tonnes of Britain's oil. And it isn't not doable, it is doable. And if we just took the military, aviation, that would be less. That one's 125 miles square, and that one's 70 miles square. It's a big area, no doubt about it, but when you compare to importing it from the Middle East, burning it, and what we're doing with it, it's doable. The times now, I want to see fuel to replace fossil. It ensures continued availability of fuel as opposed to it running out on us. And you know, when fuel runs out, you remember the slide where 89% of the oil is going to be wanted by China. You don't tell me that'll be a peaceful transition, because some countries who want a lot more oil will want to take it by force, won't they? Without mentioning their names. So there's no conflict in the use of land resources, and we can produce diesel, plastics, as I said before. And it's a good business proposition as well, which is another, the main point. Now, some of you might have heard of this trans-European DC grid, high voltage DC grid, which is proposed, not been built. And it's on consideration in Europe. The idea is that we have a planet which is hot at the middle and cold at the north. And it's windy at the north, and sometimes windy in the south. And it's sometimes sunny in the north, sometimes here. So, if you built a huge grid of DC links undersea to each country, at any time the intermittency of renewable energy would be overcome. Because when it's windy and rainy in Scotland, it might be sunny in the Sahara. And when it's, does it rain in the Sahara? I don't think so. And so what I'm trying to say is that over a big distance, you could equalise the intermittency factors. So it's not built, but I think it would be a good idea if we could build it. I mentioned that we use 140,000 tonnes a day. I mentioned burying it in the old oil wells, so that's been dealt with. Those of you who are interested in the fusion reactor, this is the tokamak reactor at Oxford. Now I've been inside that here, and it's very fascinating because there's no radiation at all. They have intense temperatures in there, the temperatures of the sun, contained with a magnetic field. And it's really, it's a foregone conclusion that they'll do it, but quite when they'll do it, we don't know. And this is the ITER project, which is the international one. It's a similar principle with the toroidal chamber. And that's the one that's running in Europe. Now, it's not French, where it's based in France, but it's Chinese, it's Russian, it's American, it's British, it's Indian, Australian. They've all put money in, all together. This is something about our lifestyle and what's happened. If you think about how long it took to get to the Industrial Revolution, it took 10,000 years of civilization, from man starting 8,000 years BC and 2,000 years AD. And then it took about 200 years to get to the, what I call the dot-com revolution. And you know, it's not far back when computers first came in and everyone said, oh, that won't work. But of course, it's now our lives, isn't it? And then the Green Revolution has started in only 20 years. And I've been at Green Revolution for 25. And I'm telling you, it is the next industrial revolution change. To make clean energy as opposed to dirty energy, we will realise it's the only way we can survive. Here's another problem we face. Anyone who can think of what I'm trying to say, shout and stop me.
Population?
Yeah, that's it. We're adding to the population of the planet. When I was born, we were 2.2 fragile. So it's very small. So we can't afford to mess about with it. Now, I mentioned earlier on about prosperity without growth. Prime Minister says, oh, we're in a mess. We can't expand by 1.5% this year. I don't think we should even try for 1.5%. I think we should stand still or minus. Now, how can that be economical? Because we should force companies to be more usable in materials and energy, so that I spent 60 years of my life making lemonade and cola. And I had a big plant, had 700 people, did 20% share of the UK market. And all of my time I was at work, I had a constant sales line increase and a profit increase through all the depressions and everything. And I thought that was good. I don't think it's good now. I think the company that will succeed in the future is the one that manages to expand its sales and its business without impinging on the Earth's resources in some way or other, reusing its waste, reusing other materials, providing people as a means of making it, and doing better, but not at a growth rate. So, most people will look at the companies that are really good at this, and like fair trade has come in now in the grocery stores, and some people respect that, and some people buy fair trade. In a few years' time, some people will only buy goods from a company that's got a good record in the environment. And the environment will become more important than the profit. And the companies that don't do it, the customer will vote with the feet and they won't have any business. Now, people say that climate change is not happening. If we actually go ahead and build the system that I'm proposing, like a universal renewable energy system, we would have created a whole new industry and cleaned up the pollution in the atmosphere. Now, if we're wrong, we'll permit the continuation of our species on the planet. And I can't think that either of those two things is bad. So whether we're right or wrong, it's good. So I think it's a no-brainer even for the Flat Earth Society. And you know who the Flat Earth Society is, I know who they are. Remember, treat the Earth well. It was not given to us by our parents, but it was loaned to us by your children, and you're not here for. So make a change. Make this university buy green electricity. Make, when you went to go to a job, make a company, tell them what you want. It'll make a big difference.